Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into a fascinating article by Jose Valim on data evolution using set-theoretic types. It's a real brain teaser, but stick with me. It's worth it. This is going to be fun.
Ooh, set-theoretic types. Sounds intense. I'm already intrigued. What's the core problem Valim's tackling?
Right, so the problem is backwards compatibility in libraries. Imagine a Rust library with a schema struct. Initially, the name field is a C string but the C spec allows null Oops! The library starts producing null names, breaking compatibility with other code that expects a string. A classic!
So the easy fix is to change the name field to option right? But that's a major breaking change for everyone using the library.
Exactly. A major version bump, potential cascading failures across dependent libraries. A nightmare scenario for maintainers. Valim explores a more elegant solution using set-theoretic types, which are, a bit more advanced.
I see. So how does this set-theoretic approach work in Elixir? He uses structs as an example, right?
Yes. He shows how, with structural subtyping, the type of a struct is determined by its value, not just its definition. Clever! So, if you have a schema struct with a string name, it's considered a subtype of a schema that allows string or nil is. Even if the definition changes, existing instances remain valid.
Interesting. But what about functions that operate on these structs? Won't they break if the type changes?
That's where revisions come in. Valim proposes adding revisions to the struct definitions. Each revision represents a version of the struct, and the type system ensures compatibility across revisions. It's like version control for types.
So if a function works with revision 1, it'll also work with revision 2, as long as revision 2 is a supertype of revision 1?
Precisely. The compiler automatically generates function signatures that enforce this revision preservation property. It's all about ensuring type safety across different versions of the data. It's beautiful, really.
But how does the compiler actually do that? I mean, that sounds incredibly complex.
Yeah, it gets a bit hairy. He talks about using set operations intersections, unions, negations to define the function signatures. It's essentially a formalization of the compatibility rules. It's quite mathematical, to be honest.
So basically, the compiler does all the heavy lifting to ensure backwards compatibility, even with evolving data structures. That's amazing!
Exactly. And it's not just about single structs. It handles multiple fields, transitive dependencies, and even allows for controlled downcasting from newer revisions to older ones. It's a complete system.
This sounds like a huge leap forward for library maintainers. No more fear of breaking changes? Almost.
There are still challenges, of course, performance implications with many revisions. And the practicality of this approach in real-world scenarios need further investigation. But the core idea is incredibly promising, a game changer.
I'm sold! This is a brilliant solution to a very real problem. Thanks for breaking it down for us.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Join us next time for more exciting discussions on the cutting edge of technology. Goodbye.
Bye-bye.